there. The purpose of this video is to do a little screen share and walk you through the process, taking a critical look at the surveillance data that we're being given from the CDC. And I want to share, basically it's an anomaly that I found, and hopefully there's somebody out there with the proper qualifications that can correct me if I went wrong somewhere. But from what I can tell, something doesn't add up, and it seems like necessarily true that we are being given numbers that are clearly inflated. So yeah, let's get started. Okay, this is the site. This is the web page where on cdc.gov, where they give us the number of cases, the number of deaths, and the number of new cases. So cases. What? It seems like a natural question is, what is a case? We just kind of take it for granted, I feel like, and we just accept, oh, it's a case. It's someone who's sick with COVID. So anyway, this is where the investigation begins. What precisely is a COVID case? Now, we actually have here. I just pulled it out on this slide, but we can look at the site. If we go to the CDC, they have the NNDS site where they give us set of criteria. There's clinical criteria, there's laboratory criteria, epidemiological criteria. And down here we get the case classification. There's probable cases and there's confirmed cases. Probable, there's some combination of the different criteria. Confirmed, it's very straightforward. A confirmed case is someone who meets confirmatory laboratory evidence. So we scroll up, that's actually up here, laboratory criteria, just a single bullet, confirmatory laboratory evidence, detection of SARS-CoV-2 RNA in a clinical specimen using a molecular amplification detection test. Now, it doesn't take a lot of research to find out that a molecular amplification detection test is a PCR, polymerase chain reaction, a test that's based on the polymerase chain reaction technique of amplifying DNA or RNA. And this is actually, so there we have it. So a confirmatory laboratory evidence, we have a positive PCR test that gives us a confirmed case according to the CDC. And this is actually consistent with the WHO guidelines. I'll show you that too. So this is the PDF for the guidance for how do you classify a case. If you scroll down, there's case definitions. They have different, slightly higher grain distinction between suspect, probable, confirmed. But if you go to confirmed, you see a person with confirmed COVID-19, a person with laboratory confirmation, irrespective of clinical signs and symptoms. So that's actually more explicit than the CDC in terms of basically saying that symptoms don't matter. If you have a positive test, you're a confirmed case. Well, technically it says laboratory confirmation, so there's still a little bit of kind of little fuzziness there. I mean, does that mean a single confirmation? A single positive test, or does it mean that they should be retested, maybe 2 subsequent positive tests? I don't know. But it's clear that it doesn't matter what the symptoms are. So I went ahead and just kind of pasted those 2 definitions in here. And this seems like a valid statement. It seems pretty clear to me that COVID case, a positive PCR test result. So a natural question to ask, how accurate is a COVID-19 diagnostic test. Naturally, if that's the criteria we're using for designating someone as a confirmed COVID case, then we should know how accurate the test is that, that makes that confirmation. So if you do a little bit of research, you can find the way that the test accuracy is kind of quantified are these two qualities called sensitivity and specificity. Sensitivity, also called the true positive rate, that's the percentage of the time the test correctly identifies an infection. And specificity is the true negative rate. It's the other side of the coin. It's the percent of the time that the test correctly identifies a lack of infection. So a lower sensitivity, a lower true positive rate means you're going to get more false negatives. And on the other side, a lower specificity means you're going to have more false positives. You kind of have to think about it for a little while to see the distinction, I feel like, just to fully grasp it. But those are the basic metrics. So there's going to be a percentage. So when you're saying that a test is, when you're asking the question, how accurate is a test, you're going to have two numbers, a percentage that says the true positive rate and a percentage that says the true negative rate, also known as sensitivity and specificity. So I went searching to try to find some reasonable numbers for the true positive rate, true negative rate for the COVID-19 diagnostic test, the PCR test. And it turns out it's actually kind of hard. It's hard to find, and I think there's a number of reasons for that. But it's certainly, like, there's no single set of numbers that apply across the board unless you think about it as an average, because let me go and show you. Yeah, here's the list of tests that are approved by the FDA for use, their COVID-19 diagnostic tests. And you can see there's a great many of them. And what's good about this website, you can go through and see the instructions for use and all of the manuals that go with the test. But anyway, so each test is going to be somewhat unique and should have its own independent testing done, but there should be some numbers out there that tell us, like, okay, here's what the true positive rate, here's what the true negative rate is. And here's just type it into Google, you say how accurate are they, you scroll down, they give you their funny little embedded answer. And I thought it was interesting because they say, generally speaking, if a test result comes back positive, it is almost certain that the person is infected. So, there's no numbers there, but they give us the idea that if it's positive, don't question it. And what's interesting is that they say if a test result comes back positive, they're not saying like, oh, if you're tested and it's positive and then you're retested and it's positive. Basically, they're basically saying that it's so accurate that it's basically 100%. Basically 100% true. Well, let's see. That's not a false positive, so that would be 100. One of the metrics is 100%, right? So if it's so basically they're saying if it's positive, it's not a false positive. So that means it has a perfect specificity. But anyway, let's not get wrapped up in that. What I want to do is look at some numbers, and it's kind of hard to find them. A lot of the websites are really focused, or a lot of the articles that I've seen are really focused on the false negatives, because that's the scary thing here. So we can even see I've pasted an article that actually does give us some numbers. Here, I should just go to the actual one. So this it is. It's on heavy. This is where it is. It's on heavy.com. You can see what. Here's the section that I pasted in. So it says that in the lab, there was 100% sensitivity on positive samples and at least 96% specificity on negative. But that's in a laboratory setting, so in the real world, testing conditions aren't perfect. So they give us a range of 66 to 80% for sensitivity. So that's good. We got some numbers to work with. We got 66 to 80% sensitivity, and we're saying 96% specificity. Great. So we got some numbers to work with. So, and this is what I was saying here. So that means nearly 1 in 3 infected people who are tested will receive false negative results. So that's the scary part. That's what I'm talking about. Like, a false positive, it's, don't worry about it. Don't worry about it. It's not even possible, or, but false negative, that's the scary one, because if you're infected, you go out and get other people infected, then, you're actually, that's a big problem. So that's what I'm finding is in all the articles, they kind of have this scary thing about false negatives, but then don't really pay much attention to false positives. So that's an interesting observation. But there's more to it. They say nearly 1 in 3 infected people will receive false negative results. But as I just said, there's more to the story. So this gets into taking the next step of analysis. There is this statistical phenomenon called false positive alarm, and there is an article on Scientific American that describes it, and it basically it's a statistical mathematical phenomenon. The article itself is actually specifically talking about the serological antibody tests, but it's mathematic. It's a statistical thing. It doesn't care what type of test it is. But basically, it's a very important fact that the true reliability of a test is dependent upon the actual infection rate. That is the percentage of the people who are being tested who actually have an infection. Now it's a little bit counterintuitive, so I'm gonna go through it, but I'm sure in case you already are familiar with it, or if you want to go read the article yourself, and not have me explain it all, I'm going to put a link in the description here so you can skip past this whole description, because it might be a little time consuming. Okay. So the way it works is we start by looking at all our possible situations here. We have true positive, true negative. We have the good outcomes, and then we have false positive and false negative, which are the bad outcomes. And just to be really clear about what that means, is true positive means someone who's infected tests positive. True negative, someone who's not infected tests negative. False negative, someone who is infected tests negative. And false positive, someone who is not infected tests positive. So I went ahead and put each of those situations here next to an icon. This is these little icons are from the Scientific American article. They're used in the diagram. We'll see those in just a moment. So from there, we actually take into account the infection rate to compute these two values, a positive predictive value and a negative predictive value. The positive predictive value is determined by considering the total number of expected true positives in the population with the total number of expected positive test results. And those positive test results are going to include both true and positive results. And likewise with the negative, it's the same thing. except we look at the total number of expected true negatives out of the total number of negative test results. Again, negative test results, those are going to be both your true and false negatives. So hopefully the next few slides walking through this will help to clarify, make this really crystal clear. Okay, so the example that's given in the article is a population of 500 persons with 25% infection rate. So we do the math, that comes out to be 125 people who are actual infections, and the rest are, so that's 25% of 500 is 125, and then the rest of them are 375 people who are not infected. So this diagram over here shows each dot is a person, and they're color coded. The red ones are the infections, and the gray ones are the non-infections. So if you count those up, there's 125 red ones. And the other part of the example is the tests that we're using. The accuracy is, we just, for the sake of this example, because we're using 95% sensitivity and specificity, just to keep it simple, both the same. So when to figure out the expected test results, we multiply the true value. So let's look at our actual, let's break down our actual infections. We have a true positive rate of 95%. So that means 95% of these 125 are true positives. So that's represented by the solid red dot here on the diagram. If you count these up, there's should be 119 here. And then the other 5%, 6.25, those are going to be false negatives. So that's represented by the red with a little gray X. So those are people who are in the original population as true infection, as actually infected, but due to the accuracy of the test, the true positive rate is less than 100%. So we have these false negatives, right? Okay, so that makes sense. So the true positive rate breaks down our actually infected members of the population into these two categories. And then on the other side of the coin, if we look at the gray area, the people who are negative, we do the math. We got 356.25 true negatives. That number, straightforward, it's 375 multiplied by the specificity, and 356. So that's 95% of 375. And then also the other ones that are negative, they give you false positives. That's 5% that gives you the false positives. So there's 18.75. So I hope that makes sense. So we're going to look at the positive test results to determine the positive predictive value. So remember, we had 118.75 true positives, and then we add in the 18.75 false positives, which gives us a total of 137.5 total positive tests from our result. So you could see the little icons show what that is. So 130 should be rounded up, 138. We got these red ones and then these little gray ones with the red X's. Those are the positive test results. So we come up with the positive predictive value by looking at the percentage of those positive test results that are actually true positives. So 118.75 true positives out of 137.5 total positive tests. And you see what we get is actually 86% that are correct. So in our scenario, where 25% infection rate, the 95% true positive rate test actually only gives us 86% correct results. So we call that 86% positive predictive value, which means that 86% of the positive tests are true positives. Now, it's basically the same exact logic for the negative predictive value, except we look at the negative outcomes of the test. So we recall from our original calculations, we had 356.25 true negatives. Here, I'll go back just to show where that number comes from. This is the earlier slide. See how we got these 356.25 true negatives. That came from our multiplying the true negative rate times the number of people who are actually in the population that are negative. So that gave us that many true negatives. We take that, we add in the false negatives. We'll go back here. The false negatives were the ones that were actually positive in the population, but due to the true positive rate of the tests, we gave us a false negative. So we're looking at that number. Add those together, we got 362.5 total negative tests. So that's going to be these little red ones here, the ones that were positive but got a false negative, and also all the true negatives. So out of all of the negative tests, we had 356.25 true negatives out of 362.5 total negatives. Actually, there's 98% correct negative results. So when the test gave a negative result, it's 98% were true negatives. Only 2% were actually false negatives. Does that make sense? It might make sense. If that's not clear, I'd say pause the video and go read, go read through the article and look at these more closely, and or go back. You can go back and listen to my explanation again. I don't know how good my explanation was, so, but anyway, so to summarize our example, we had a population with 25% infection rate. 25% of the people in our population were actually infected. We used a test that had 95% true positive rate and 95% true negative rate. With those parameters, we expect that a positive test result is going to be accurate 86% of the time, so that it'll have an 86% positive predictive value. And likewise, the negative test result are accurate 98% of the time. So our negative predictive value is 98%, which is interesting, considering we started with a test that had both of these 95% accuracy. So yeah, if you go look at the article, they show that in contrast to a, here I can just pull it up right now. So here they show it with a population with only a 5% infection rate. And it's actually much more dramatic, the difference. We see that in this scenario, an individual who tests negative is 99.8% chance of being a true negative. And then we scroll down, but an individual who tests positive only has a 50% chance of actually being positive. So the positive predictive value for this test, when the infection rate is 5%, is a meager 50%. That means a false positive is 50-50. So, which is pretty amazing, because again, we are using a test that is 95% accurate on both positive and negative. So that's how important this concept is. So here we go. Let's experiment. I've created a spreadsheet that shows the expected positive predictive values and negative predictive values for a given true positive rate, true negative rate, as well, and then also various infection rate. And now what we'll do, so let's go back to remember that article for the COVID diagnostic estimates. So we'll use the estimates that were given in that article of 80% true positive rate, 96% true negative rate. So we're using the specificity, the true negative rate from the lab test, the laboratory setting test, and we're using the high end of the kind of real world true positive rate here that he gave. So he said it's a range of 66 to 80. Let's go at the top of that. We'll assume the best. So we'll plug into our spreadsheet these two values. Okay, so here's the spreadsheet that I created, and here's how it works. So you see we have up here the true positive rate, the true negative rate. We set it to the values that were given in the estimates that were given in the article. 80.8, that's 80% sensitivity, and then 0.96, 96% specificity. And then down here in this first column, I just generated all of the percentages 1% at a time. So here is 0.01, that's 1% of the population is infected. We go 1, 2, 3, 4, 5, and increment it by 1% until we get all the way to 1, which is 100%. So you can see those. So we're going to see the scenario for each. We're going to look at the negative predictive value, positive predictive value for each percentage, And then these columns in between are true negative, true positive, false negative, false positive. So each of these they multiply the infection rate by the appropriate value from the true positive, true negative rate. I won't go into super detail about this. I'm going to share this spreadsheet in the description so you can look at this yourself and you can poke around, see specifically how it works. I just wanted to show you. I found this blog article of someone who actually wrote a little bit of code that actually demonstrates this. They give a little explanation from the Scientific American article, and then here's a little bit of code that actually does the calculation. You give it the true positive, true negative rate, and then infection rate, and it generates everything. So you can look at that if you want to see the nitty-gritty details, but it's just what I showed you in that example. So it breaks down a given infection rate into true negative, true positive, false negative, false positive, and then it does the computations to give us the various predictive values. And I went ahead and I made a copy of the spreadsheet here. So this is just a duplicate so we can mess around a little bit more freely, because I want to leave this as showing the example. So we have this other sheet down here that's just a copy, and so we can kind of test out the extremes to validate that this is actually working properly. So let's say, for example, I have 1 and 1. That means perfect true positive rate, perfect true negative rate. And then if we look at all our values, whatever the infection rate is, the positive and the negative prediction values are 100% all the way down, except you get a divide by 0 when you have 100% infection rate, because if there's no one that isn't infected, then you can't have any negative. Anyway, you get the idea. So if we change it to a really low, say we do a 1% true negative rate, what that means is we're going to get a bunch of false positives. but we're always going to have a perfect true positive rate. So if someone is negative, it's always going to perfectly say, it's always going to give you the right answer. But if someone's positive, it's going to be pretty horrendous all the way down. So you can kind of see until you get up to a really high infection rate. Likewise, if we say perfect true negative rate, and we say we give you a 1% true positive rate, you can see we get, perfect positive predictive value. So I think that's just to kind of validate that we have the equations in there correctly, and intuitively it makes sense. Perfect true negative rate means we have no false positives, which means it is 100% false positive predictive, 100% positive predictive value. Okay, hopefully I didn't belabor that too much. Okay, so let's start looking at the actual data. Now, we've got our numbers in. These are our estimates for the accuracy of the test, and I should mention that the article that we're getting these numbers from was written by an associate professor of biology at Rochester Institute of Technology. So not just some random dingus who's just pulling stuff out of their ass. This is, someone who's qualified to write on the topic. So I think we have reasonable estimates for what the actual accuracy of the COVID diagnostic tests are. And so let's take a look and make some observations. So one thing that stands out to me is that you see the negative predictive value is 95% or better, all the way up from 1% infection rate all the to 20% infection rate. So that means that if you get a negative, so let's say if the infection rate of COVID-19, that is of the population being tested, if 20% of them are actually truly infected, then that means that someone who gets a negative test result is 95% probable that that's a true negative. However, at 20% infection rate, the positive predictive value is only 83%. So what that means is that in that population where there's a 20% infection rate, someone who receives a positive test result is actually only 83% likely to be a true positive. It's almost, about 17% likely that it's a false positive. And notice as the infection rate goes up, the negative predictive value goes down, but the positive predictive value goes up. See? So by the time you're at 50%, if you have a 50% infection rate, then that means a positive test result is 95% likely to be a true positive. But the negative is only 82%. So, to me, well, first of all, this gives us a really pretty strong idea of how important the true infection rate is when looking at interpreting the value, interpreting the results of tests. Because if you get down here to only 6%, it's no better than a coin flip. If you get a positive test, it is slightly better than coin flip. So to me, the natural question is, what is the true infection rate of SARS-CoV-2 of the population that's being tested? Ideally, we'd only be testing people who are highly likely to have the infection. So that would mean our infection rate would be higher. So my point of saying that is this infection rate, we're not necessarily talking about the entire population. We're talking about the population of people who are receiving the test. So so that's the question. How high is it? And it seems like it would have to be pretty darn high to have a strong confidence that a single test result is indicative of an infection. A single positive test is indicative of infection. See what I'm saying? So the question is how do we figure out what that true infection rate might be? Now, that's intuitively that's a hard, difficult question to answer, just due to the fact that the mechanism by which we determine the infection rate is the test itself. So you can't really use the test itself to judge the accuracy of the test itself. I could be wrong. There may be techniques for doing that. This is kind of where we're getting into questions that I'm putting out there for someone who knows. So how can we have a reasonable estimate of the infection rate of the people who are being tested? Because let's just take a look here. So I have the CDC stats here I pulled in, and I got the links here from the source. But yeah, basically here's the number of tests that were reported, the total of a number that were positive, and then so 8.6% of all the tests that were reported to the CDC are positive. So are we to interpret this to mean, or to kind of think that this is a ballpark estimate of the actual infection rate? So if 8.6% of the tests are positive, then is that close to what the true infection rate is? Because if we plug that sucker in there, 9%, that gives us a PPV of only 66%, 2/3, which seems incredibly low. Which that means that the overall case numbers are inflated by 30%. And by the way, this little block up here, what I did was I pulled in the data from this other sheet. So the test results, the positive tests, I pulled those in, multiplied them by the true positive, true negative rate. So you could see 80% of the total number of positive tests as this number, and then 96% of the negative tests is this number, to give us, the idea is just to adjust those numbers based on the true positive, true negative rate, and then just see what that percentage comes out to. And it's actually a lot lower. So, but say we even double that. That's the thing. Let's double that. Let's say everyone was tested twice. Get 14% infection rate. We're still only looking at 3/4 of the positive tests being true positives. I know that logically is not quite sound, because if you test someone twice, that changes the probability. But yeah, so that's the question. How, what is a reasonable estimate for the infection rate, and how does this reconcile? The CDC is telling us that 100% of positive tests are in fact infections, yet this clearly indicates that there's a significant number of those that have to be false positives, even if the test is super accurate. And by the way, let's look at the lower end of this here. 66% true positive rate, that was the lower end. Let's see how far down that jumps. See, now I guess it's not so dramatic, but 72%, 14% infection rate. Anyway, so I invite you to you know, to go ahead and download the spreadsheet and mess around with it and understand what the heck's going on here. And then so for the average person, you know, grab this spreadsheet and try to understand what I'm saying here. And then for the you know, if there's any epidemiologists or any, you know, mathematicians or anyone who can shine some light on this anomaly, by all means correct me. I will receive I will gratefully receive any criticism or clarification on what's going on here, and I will publish a follow-up video that, you know, to describe, you know, to correct anything if there is anything to be corrected. Okay, to kind of to close this out here, I wanted to put a couple of notes, observations out there. This is all data. I put these little blurbs in the links, or in the observations. There's a tab here, and it has some links that kind of verify what I'm saying. So, you know, I'm not just pulling this stuff out of my ass. 80% of infections are mild or asymptomatic. 80% of COVID deaths are older people, age 65 plus. 94% of those deaths are, in fact, not COVID alone, but they include comorbidities. And then finally, there's no set of symptoms that are distinctive to COVID-19. That is, there's varying symptoms of respiratory disease that could be attributable to other diseases. So, I mean, looking at all this together, it also kind of makes me scratch my head thinking that, so if 80% of the infections are mild or asymptomatic, is it possible that, say, I don't know, half of those are false positives? That seems reasonable. Say half of the people who die are actually not infected at all. You know, given the accuracy of the test and the unknown infection rate and the unknown all the unknowns. Yeah, so I mean, I'm not saying that this thing isn't an issue and that there's not a virus that's you know, causing suffering out there, but it's my suspicion that, you know, it's overblown. I mean, it's exaggerated, and you know, it's pretty clear to me that the media is you know, trying to scare the hell out of us. And yeah, from where I'm sitting, I question that. Anyway, thank you for watching, and I will be glad to incorporate any feedback and you know, go back and make another video to incorporate corrections and things like that. Thank you very much.